Last episode, we trained a real MLP on real data. And to keep things simple, we did something a little reckless. We shoved the entire dataset into the model in one giant lump. That works when your data is a few thousand rows. It falls apart the moment your data is bigger than your memory. So today we build the part of PyTorch that every serious training loop leans on, the data pipeline, and then we hand the whole thing to the GPU and watch it fly. Remember what we did last time? We fed the whole array at once, model X, where X was everything. It's fine for a toy. But real data sets, millions of images, gigabytes of text, will never fit in memory all at once. We need a way to stream data in manageable pieces. Those pieces are called batches. Why batches? Two reasons. First, memory. A batch of 64 fits comfortably where the full dataset wouldn't. Second, and this is the surprising one, batches actually train better. One example at a time gives you noisy, jittery gradient steps. The whole dataset at once is smooth but painfully slow. A batch of 64 is the sweet spot, smooth enough to point the right direction, small enough to take a step every fraction of a second. So, how do we describe a dataset to PyTorch? With a tiny contract, two methods. Len answers, how many samples do you have? And getitem answers, give me sample number I. That's it. PyTorch doesn't care if sample I lives in memory, on disk, or behind a network call. As long as you can fetch it by index, it's a dataset. Now, the star of the show, the data loader, think of it as a conveyor belt bolted onto your dataset. You hand it your dataset and a batch size, and it does three jobs at once. It groups samples into batches, it shuffles them, and it can even load the next batch in the background while the GPU is busy. One object, three superpowers. That shuffle flag matters more than it looks. Shuffle true means the data loader reshuffles the order at the start of every epoch. Why? Because if the model always sees example 1, then 2, then 3, it can quietly start memorizing the order instead of the pattern. Reshuffle every pass, and that crutch disappears. Two more knobs worth knowing. If your dataset doesn't divide evenly by the batch size, the last batch is a short leftover. Drop last at truth rows that run away when you need every batch the same size. And num workers spins up helper processes that prepare the next batch while the GPU chews through the current one. So the GPU never sits there waiting for data. Now the GPU itself. Here's the one rule that trips up everyone. Your model and your data have to live on the same chip. If the model is on the GPU and the batch is still on the CPU, PyTorch throws a device mismatch error and the whole thing stops. The fix is two lines, model.toDevice once and batch to device every loop. Same chip, no crash. And here's the payoff. The exact same training loop, same model, same data, same code, runs on CPU in 38 seconds and on the GPU in 4. That roughly 10x speed up is the matmul parallelism we talked about back in episode 1 finally cashing in. And it only shows up because we made the model big enough to keep the GPU busy. The pipeline's ready, clean datasets, batched, data loaders, everything on the GPU. Now we point all of it at language. B0 overview. Here's datapipeline.p is 3 pages. Page 1 builds the pieces. A custom dataset, a data loader, a wide model, and the device selection. Page 2 is the time training loop. One function that trains for n epochs and reports its wall clock time. Page 3 runs it twice, once on CPU and once on GPU, and draws the bar plot that compares them. Let's walk it. Up top, the imports, including matplotlib for the plot at the end, and a synthetic dataset. We make a 2-feature blob with torch.random and a simple linear rule for the labels. 60,000 samples this time. We need real volume so the GPU has something to chew on. A toy-sized job would actually run slower on the GPU. Here's the contract in code. Toy dataset subclasses torch.utils.data dataset. Len returns the number of rows. getItem takes an index and hands back one XY pair. That's the entire dataset. 3 short methods. Now we wrap it. DataLoader dataset, batch size 64, shuffle true. 60,000 samples over batches of 64 gives us 938 batches per epoch, reshuffled every time. This one line is the conveyor belt from the animation. A wide model and the device pick. Device summon torch.device CUDA if torch.CUDA is available, else CPU. Best chip available with a fallback so the code runs anywhere. We print it so we can see exactly where we landed. Page 2. Here's train epochs. We move the model onto the device once, build the optimizer and start the clock with time, perf counter. Then we loop epochs, and inside each epoch we loop the loader. Notice the very first line in the batch loop. xb, yb, xb to device, yb dot to device. That's the dot to device fix in the wild, moving each batch onto the same chip as the model. The rest is the loop you already know. Forward, loss, zero grad, backward step. At the end we return the elapsed seconds. Page 3. The experiment. We call train epochs once with the CPU and once with the GPU. Same function, just a different device. And capture the 2 wall clock times. We print both totals. Finally, we plot them. A 2-bar matplotlib chart, CPU versus GPU, written straight from the 2 timings we just measured. Peltart bar, CPU, GPU, CPU sex, GPU sex. Same code, 1 bar 10 times shorter than the other. The pipeline's ready and it's fast. Next episode we hit the wall that every language model starts with. Text. Raw text is the enemy, and tokenization is how we beat it.